All right, hello everyone. So today we have a linear algebra problem. I'm trying to find the singular value decomposition of this matrix A. A is equal to this 3 by 2 matrix here. And when you're asked to find the singular value decomposition of a matrix, you're looking to rewrite A as a product of three matrices. These three matrices are U, sigma, and V. And at the end, you're going to take the product of U, sigma, and the transpose of V, or V transpose, and all that together would give us A. So a couple of things to recall is, to know is that in terms of the size of the matrices, U is M by M, sigma is M by N, and V is an N by N matrix. Yeah, both U and V here are orthogonal matrices. And A is as well M by N. I didn't see what the size was, but we're going to just assume that it's an M by N matrix here. Let me just write that down just right here. Okay. Now, before I get into the video here, before I get into the problem, I want to say a couple things. You will need to know how to find eigenvalues and eigenvectors here, because unfortunately we don't have enough time to go over that. So I'm assuming you have knowledge of that, and if don't, I would stop this and go over that. So just be aware of that. And also I'm going to do some stuff with not so important, but with like finding cross products and such. So if you need to review that, please go ahead and do so. But for the most important thing here is finding eigenvalues and eigenvectors. So it's multiple steps here. Okay, there's like 5 main steps to form these matrices, V, sigma, and U. So the first thing we're going to do is we're going to go up to number 1 here. And number 1 and 2 are, in my opinion, the most important steps in this process. You're going to form A transpose A, and you're going to go ahead and, after that, find the eigenvalues of A transpose A. Okay? And for A transpose A, real quick, that's a symmetric matrix, and it's orthogonal. And the eigenvalues are going to be non-negative, meaning that they're going to just be positive or 0, but no negative eigenvalues or complex. Okay, and I have 3 other steps here, which I'll get into more. Let's go through the first 2, which is, first of all, I'm going to find what A transpose A looks like, okay, which, by matrix multiplication is what you see right here. Step 2, I'm going to find the eigenvalues and the eigenspaces that correspond to the eigenvalues. So you take your matrix and you subtract it by lambda I and take the determinant of that. So that's how we find the when we set this all equal to 0. And that's how we find our eigenvalues. And at the end of the day here, you're going to have lambda equals 80 and lambda equals 5. And typically, when you have the equation can get kind of complicated, usually if you'll get a quadratic or a cubic of the sorts. So just be prepared for that. That might take you a couple minutes to factor and to solve. And what we're going to do now is this. We're going to find the eigenspaces for each of these eigenvalues. So if lambda equals 80, you take your lambda equals 80 and you plug it back into this right here, this expression, but as a matrix. And you would row reduce, and your eigenvalue would come out to be 2, 1. And sorry, your eigenvector, 2, 1. But we're going to go ahead and normalize it, or make it into a unit vector. We do that by taking the squares of the components, so 2 squared plus and 1 squared, and adding them. So 4 plus 1 is what you get inside, which is 5. So it's the square root of 5. And you divide each component by the square root of 5. Okay. So there you go. Now, that would be your vector here, and we're going to just hold on that to the second. For a second, I'm going to do the same thing with lambda equals 5. Again, I'll put lambda equals 5 back into our matrix that you see over here, and we do the same thing pretty much, and now you get a eigenvector of -1/2 and 1, okay? And again, plugging back then, row reducing, and that gets us down here. And what I did was I multiplied that eigenvector by 2 so I can get rid of the fractions. And you get -1, 2 from that. And I'm going to do the same thing. I'm going to normalize it. And you get -1√5 and 2√5 as your eigenvector. Okay, so for V, the first step is, the way you form V, our first matrix, it goes to step 3, is you form the columns of your eigenvectors. Your columns of V are going to be the eigenvectors that you just got for each of these eigenvalues. So, and it's really important, you have to put these in order from largest to smallest, left to right. So I'm going to put the largest eigenvalue, which is 80, and under lambda equals 80, you're going to make the column here is going to consist of the eigenvector or vectors that you get from 80, which is those two. And the same thing for lambda equals 5, but it's important that you put these in order from largest to smallest. Now, so that's what V is, that's what V consists of. For sigma, so I wrote the instructions on how to find sigma. So sigma is going to be the same size as A, and it consists of basically a matrix D, that's what that D is. It's a diagonal matrix and a bunch of zeros, okay? And here's how this works. So I wrote the rule, but I'm gonna kind of go with something a little easier. This diagonal consists of what we call sigma 1, sigma 2, sigma r, which are the square roots of the eigenvalue. So sigma 1 would equal the square root of the first eigenvalue being the largest, so that entry would go here. And then the next eigenvalue that we got was 5, so it'd be the square root of 5 for the next one, and etc. And these would go on along a diagonal. Well, that's it. That's the only ones that we got. So the diagonal matrix is formed as such, and this value of sigma, this matrix sigma is the same size as A. So A is 3 by 2. So what I'm going to do is I'm going to just put zeros everywhere else in your matrix to look like a 3 by 2. Okay. Officially, what I did was what you see written there right above it. Those words were the m minus r rows and the n minus r columns. So the D there just stands for this part that I wrote over here. And then what the m minus r rows and n minus r columns here stand for is the number of rows and columns of 0 that you would have that you need to make that matrix sigma to be the same size as A. Okay, so we got that for sigma. And yeah, I mean, those are the instructions, as I said, right above this result, but I find it a lot easier just to go over what we did in the first time. Is just to write out the eigenvalues and then on the diagonal and put zeros everywhere else. And they and only the positive ones, by the way, as well. Only the positives. If you have one of 0, that doesn't count. Now we're going to form U. And U here is made up of columns, which consist of, not entirely, of these two expressions that you see here in red. U1 and U2 here. So U1 is 1 over sigma 1, or 1 over the square root of the largest eigenvalue, 80. The vector A times V1, which is the first column of V. And you multiply that out, and you get 4/5, 0, 3/5. For your second value of U2, you do the same thing, and you get -3/5, 0, 4/5. However, here's the issue. We need to extend this to be a basis for R3. Since U1 and U2 are in R3, we can use a cross product. Yeah, and you always need to have your vectors, whatever space then, you have to form a basis, and sometimes you don't have enough vectors like it is in this case. So I need one more vector, and I can do that by doing a cross product, because the cross product would be linearly independent to these vectors which are already linearly independent within themselves. And yeah, you just form U by taking each of those columns you got, U1, U2, and then the cross right here. And that would be your U. And all of that put together, U times sigma times V transpose would give you A. All right? Thank you so much for your time. I hope this helps.